today we're going to be talking about specific heat. So what is specific heat? And specific heat is a property of matter, and it is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So like density, it's an innate property of matter that can't be changed, and it is specifically the amount of heat required, or heat or energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So specific heat can be found by the equation Q is equal to mc delta T, or Q equals mcat, as it might be helpful for you to remember, where Q is our heat, it's energy, M is the mass, delta T is the change in temperature, and C is the specific heat capacity. All right, and the specific heat capacity would be a constant that is given to different materials or objects or substances, and it's known to that. It's a known value. It's an actual value that you can look up for different properties or different objects. So specific heat and changing temperature. Specific heat can actually be thought of as a measure of thermal inertia, where inertia describes how easily something can accelerate. So the lower the inertia, the easier it is to accelerate. Something with a higher mass has a higher inertia and is therefore more likely to keep going and not accelerate. When you refer to that as a thermal inertia, then it could also be described as how easily something can change its temperature. Something with a high specific heat is more likely to stay at the same temperature, so it's less likely to increase or decrease in temperature. So for example, kind of a real world experience with this is that you've got a pizza, okay? On a pizza there's a crust and you have the cheese and sauce. Right after it's taken out of the oven, which has the higher specific heat, the crust or the cheese and sauce? And so think about it like this. What is it harder to lose temperature? Or what stays hot? What doesn't change temperature as quickly? So think about that for a second. Go ahead and pause the video. Alright, so for me this is a bit of a speculative question, because you can experience different things. You may have different opinions on what pizza feels like out of the oven. But from my experience, the cheese and sauce tend to cool off a lot more rapidly than the crust. Therefore, since it's more likely to stay at the same heat, the crust would have a higher specific heat than the cheese and sauce. Alright, let's look at some chemistry examples. Or actually, let's talk about units of specific heat first. So the specific heat is measured in units called joules per gram degree Celsius, or calories per gram degree Celsius. We're typically going to be working in joules per gram degree Celsius, but I wanted to give them both to you. And joules and calories are related by the following. 1 calorie is equal to 4.18 joules. Alright, let's talk about the details here. So Q is the heat. It's the energy transferred between two objects, one hot and one cold, due to the difference in temperatures. And it's measured in joules or calories. M, it's the mass of the substance in grams. C, the specific heat, is the energy it takes to increase 1 gram of a substance by 1 degree Celsius, so joules per gram degree Celsius, or calories per gram degree Celsius. And then delta T, which is the change in temperature, and that is the final temperature minus the initial temperature. TF minus TI, and that's measured in degrees Celsius. The delta there stands for change in. So let's talk about an example. How much heat is required to raise 100 grams of water from 50 degrees Celsius to 70 degrees Celsius when the specific heat of water is 4.18 joules per gram degree Celsius? So the equation we need to use is Q is equal to mc delta T. And let's break it down a little bit together. We're going to work through this example together, and then I'm going to have you pause the video and do an example on your own. So Q, we're asking for how much heat is required. So the Q would be equal to our mass, 100 grams of water, times our specific heat of water, so 4.18 joules per gram degree Celsius, times our change in temperature. Our final temperature was 70 degrees, and our initial temperature was 50 degrees. So 70 degrees Celsius minus 50 degrees Celsius. When you do this all together, you're going to wind up with 8,360 joules. Sorry, I want to annotate something for you guys. I don't know why that disappeared. Okay. Alright, so let's get back. Okay, so something that I want you guys to note here is that the grams here cancels out with the grams here, and the degrees Celsius cancel out with your degrees Celsius, leaving you with joules on top. And the reason the grams and the degrees C are able to cancel out is because this is joules over grams degrees Celsius. So grams and degrees Celsius are both on the bottom. Okay. I wanted to make sure that we got that clear. Okay. So, this is an example I'd like you guys to work on. How much heat is required to raise 1.00 times 10 to the 12 grams of aluminum from 50 degrees Celsius to 70 degrees Celsius when the specific heat of aluminum is 0.900 joules per gram degree Celsius? So please pause the video and work on this yourself. You can refer back to other notes or to other slides if you need to. Alright, now that we're back and you have done the work in front of you, I hope, let's go through it together. So again, we're going to be using Q is equal to MC delta T. Our Q this time is going to be equal to 1.00 times 10 to the 2 grams of aluminum times by the specific heat of aluminum of 0.900 joules per gram degree Celsius multiplied by the change in temperature, which is 70 degrees Celsius minus 50 degrees Celsius. And when you multiply all that together, you're going to get 1,800 joules. Okay? One of the other specific heat ways that we use specific heat is to determine a change in temperature from an equilibrium. And in this time, we have a hot side of the equation and a cold side of the equation. So for example, if there are 100 grams of aluminum and 100 grams of water, and the aluminum has been heated to 70 degrees Celsius, and then put in the 30 degrees Celsius water, after a while, the aluminum and water have reached equilibrium temperatures. They're at thermal equilibrium together. What is that thermal equilibrium temperature? And here the hint is that TF will be the same for both at equilibrium. So if the final temperature of both will be the same, an equation can be set up as follows. Negative Q hot is equal to Q cold. And the reason why the Q hot is negative here is because heat is going to be lost from the hot side as it cools down to reach thermal equilibrium with the cold side. And so that can be expanded to say that negative and then all of M hot C hot times the change in temperature is equal to M cold C cold times the change in temperature. The trick here, if you're going to use this method, is to make sure that you're keeping track of your negative, and a lot of people can get confused by that. So I'm going to show you another method of working through it, but I wanted to present this for you as well. So to plug it in, on our hot side we have the aluminum where we had 100 grams of it. Its specific heat is 0.900 joules per gram degree C, and its final temperature is unknown right now, but its initial temperature was 70 degrees Celsius. And that's set equal to 100 grams of water with a specific heat of 4.18 joules per gram degree Celsius, and a final unknown temperature, because that's the same unknown temperature that we're looking for, and its initial temperature of 30 degrees Celsius. If you multiply some of that in, we can condense it to negative 90 joules per degree Celsius times the temperature change is equal to 418 joules per degree Celsius times the temperature change. And here I just got rid of our gram units. I multiplied in our 100 grams by our specific heat. If I carry that specific heat and the joules per degree Celsius into the change in temperature, you're going to get negative 90 joules temperature final minus 6,300 joules is equal to 418 joules times final temperature minus 12,540 joules. And here are degrees Celsius from, here it is, this degrees Celsius and this degree Celsius cancel each other out. Same as over here, where a degree Celsius cancel each other out, leaving just the joules down here. Alrighty, and if we continue, if we continue with that, if we carry out the negative, we get negative 90 joules times the final temperature plus 3,600 joules equals 418 joules with the final temperature minus 12,540 joules. If you add this negative joules temperature final over to the other side, we're going to get 6,300 joules is equal to 508 joules times the final temperature minus 12,540 joules. If you add 12,540 joules to both sides, you get 18,840 joules is equal to 508 joules times the final temperature. We divide by 508 joules on both sides. Our temperature final is equal to 37.09 degrees Celsius. One of the best ways to then determine if you calculated this correctly, did you carry out the negative and all that, is to make sure that your final temperature is greater than your initial temperature on the cold side. And so 37.09 is greater than 30, so I know that, and less than our temperature initial on the hot side of 70, and so I know it's in between, which would be that thermal equilibrium temperature. So this same equation can be set up using a different method. It can also be set up as Q hot plus Q cold is equal to 0. And same thing here, where you're going to have M hot, C hot times the change in temperature plus M cold, C cold times the change in temperature, and setting that equal to 0. That should be equal to 0, guys. Sorry, I don't know where that went. So if we plug in all the information, we have 100 grams of the aluminum times the aluminum specific heat times the change in temperature with that initial temperature at 70 degrees Celsius plus the 100 grams of water times specific heat of water times the final temperature minus the initial temperature of the water, all equal to 0. If you carry out some of this, you're going to get 90 joules per degree Celsius times the change in temperature plus 418 joules degree Celsius times the change in temperature is equal to 0. We're doing the same thing here, except for we don't have that negative to concern ourselves with. So then we're going to get 90 joules times the final temperature minus 6,300 joules plus 418 joules times the final temperature minus 12,540 joules. Carrying all that math out, you get 508 joules times temperature final minus 18,840 joules is equal to 0, where we just combined our final temperatures with the joules and just our straight up joules. You get 508 joules times temperature final is equal to 18,840 joules. Dividing by 508 joules, you get temperature final is equal to 37.09 joules. So this is going to be another math heavy section of the course, but specific heat is something that we're going to look into more as we go on later. So I just wanted to kind of talk to you about it as an intrinsic property of matter, just like we talked about that there are many properties of matter in the solids, liquids, and gases online notes. Density is one property of matter, but so is specific heat. And so I wanted to give you guys a chance to kind of calculate it and determine it and figure out what it means. So we're going to do a lab on this on Wednesday or Thursday this week, which is going to be pretty fun, and I think you'll enjoy it. So tomorrow we're going to be working on practicing these calculations. If you didn't practice the calculations during the first run through of the online notes, I highly suggest that you practice them tonight during a second run through, and we will practice it more tomorrow. All right, you guys have a good night. I don't know, where am I? There it is. All right, guys, have a good night.